So, what have we done so far? We spent some time proving Besicovitch theorem. And the way that we can summarize that is that we had that dynamically defined set, and we actually proved in some detail that the Hausdorff dimension of that set was essentially, in the case of two symbols at least, where mu was an ergodic measure that supported that set. Okay? You can think of this number here, as we pointed out last time, as the entropy of the measure divided the Lyapunov exponent of the measure. In the case I was considering, the Lyapunov exponent was constant for every measure because the slope was equal to 2 in all the cases. You see, it was a map like this. Okay, so the slope was 2. And therefore, the Lyapunov exponent for every ergodic measure was equal to log 2. We proved this in some detail using thermodynamic formalism, but the general spirit of it holds true in much more generality. The idea, what you would like to normally do in this kind of situation, is that if you have a dynamically defined set, J of alpha, what you would like to have, and what you aim for, in lots of cases, is to have some sort of variational formula of this type. Okay? That's what you would like to prove. That basically, if you look at all the ergodic measures seated in that system, and you compute the Hausdorff dimension of them, then that actually gives you the Hausdorff dimension of the whole set that you were looking at. We actually did a bit more. In the case of Besicovitch, we exhibited a particular measure for which this supremum was actually attained. And it was like this. But this is a non-trivial result in general, because the Hausdorff dimension here, even though this variational formulation is true, what is not true in general is that the Hausdorff dimension, as a function of the measure, is aposemi-continuous. So, you pick a sequence of measures for which you get the supremum, but you take the weak start limit of those measures, and it might happen that the limit has Hausdorff dimension less than the Hausdorff dimension that you obtain here. So it's a difficult problem in general to find a measure that maximizes this expression here. So somehow, what I want to point out today is that there is actually two main problems when you try to apply the thermodynamic formalism techniques to show this type of results. On the one hand, you have to show some sort of variational formula of this kind. And on the other, if possible, you would like to exhibit some particular measure that actually attains the supremum. But those are two different problems, and the nature of them is also different. Okay? I would say that thermodynamic formalism would help us enormously when you try to find out the measure that maximizes this expression. And as we did in the case of Besicovitch, we realized that actually a measure that maximizes this expression corresponds actually to an equilibrium state, to some potential that you choose in a smart way. The way of choosing the potential, of course, depends upon the problem you're trying to solve. In the case that we were dealing with, it was the frequency of appearance of certain digits in the base M expansion. And, well, we constructed a potential that was well suited to that problem. And we found an equilibrium state for that particular potential that actually attained this supremum. But let me point out that in general, This is a hard question, and it's not always true that you can find. It's perfectly possible to have a variational formulation of this kind and not to have a measure that actually maximizes the expression. Okay. So what I'm going to do today is to keep on studying problems of the same nature, but now in a context that is much more complicated. I introduced yesterday the Gauss map, so I will try to formulate a problem and to sketch a proof of a result that goes along the same lines of this, but which is harder. It's technically harder, but the principle, the ideas that you have to deal with are essentially the same. So since it's harder, I will only sketch the proof, but you can keep in mind that all the details that I did when I proved this case. And with that in mind, you will see that what I'm doing is actually not completely crazy. So let me remind you what the Gauss map was. Oh, let me call it T better. It was a map defined from here to here. I already pointed out that the domain is not compact. And you had this. We discussed it briefly yesterday. We showed that there exists an absolutely continuous invariant measure, the so-called Gauss measure, and that is a system that it has infinite entropy. That was an argument, very easy argument. You cut it the first n branches, that has log n entropy. You start adding branches, and therefore the entropy of the full system was infinite. There is a very good description of the pressure of the Gauss map with respect to a particular very important potential, which is minus the log of the derivative. So let me give you that result. So let T be the Gauss map. Then the function that to each parameter T assigns the pressure of minus T log of the derivative has the following properties. It's infinite if x is less or equal than 1/2, and if t, sorry, and it's real analytic strictly convex and strictly decreasing if t is larger than 1/2. Let me make a picture. You have t here, and here you have p minus t log of the derivative. So this is infinite up to 1/2, and then the pressure looks like this. It cuts here at 1. Okay? So again, as I showed last time, in this part at least, the pressure is real analytic, strictly convex, and strictly decreasing. Exactly the same properties that we had in the previous case. Nevertheless, all this part here is much more complicated. It's actually infinite. The proof of this theorem is not easy, but to try to convince you that it's actually true, we can think of a linearized version of the... So, a remark. So to prove this, you require heavy machinery like transfer operator argument and so on. But in the case of a linearized version of the Gauss map, you can actually explicitly compute the pressure. And the pressure has the exact same properties as this one. Think of the following map. You have the same partition as in the Gauss map, I mean 1 over n. And then in each branch, instead of having something that looks like 1 over x, you just have straight lines. Okay? So this map is defined in the following way. Let me call it f. And the slope should be n times n plus 1 x and, well, minus n plus 1. Well, something like this. The slope is n times n plus 1. That's the important thing. In 1, no, this is not working. In 1, this is, of course, if x belongs to 1 over n plus 1n, I guess. Something like this. A linearized version of the Gauss map. You can explicitly compute everything because you actually know what is the derivative. The derivative is constant in each of the intervals of the partition. Therefore, what you have is that the function that, how did I call it, f prime, is actually the log of the sum is this. So of course, if t is 1/2, this explodes. This is like 1 over n squared. If t is 1, the sum is actually 1, therefore the log of the sum is actually 0. So you get a shape that is essentially the same thing as this one here, right? Moreover, in this setting here, you can show that for each t larger than 1/2, there exists an equilibrium state for the potential minus t log of the derivative. And that's nothing but the Bernoulli measure obtained here normalized by the full size of the interval. It's a Gibbs measure, essentially. But what is important, though, then, is that for every t larger than 1/2, there exists an equilibrium measure for minus t log of the derivative. Right? You can actually compute it. In that case, the measure mu t of the interval 1 over I plus 1, 1 over I is 1 over I plus 1 I power of t divided by the sum of 1 over n plus 1 t n to infinity. It doesn't matter. What is important, though, is that for t equal 1, for example, in this case, what you obtain is the Lebesgue measure. The Lebesgue measure is invariant and ergodic, and that plays somehow the role. Yes? Yeah, okay. Well, that's the exercise that you're supposed to have done already. No, but okay. I mean, yeah, okay. Oh, well, I mean, but it's simple. It's just a combinatorial argument. It's a combinatorial argument. You think of two symbols, and you get a plus b to the power of n, and expand that. And the expansion of that will give you all the possible combinations of symbols, all the periodic orbits of length n and then you just divide and you obtain this kind of formulas. It's a simple combinatorial argument. No, don't worry. Okay. Exactly. If you have another function that and gives you another sequence here of the potential for which it diverges, there is a critical value for which it diverges for smaller values of that, and it converges for the other ones, you might have a shape like this. Now, let me point out that the situation is not that simple. Depending on the sequences that you choose, you don't always get a picture like this. So it might happen that you get a picture like this. So you're infinite, and then you become negative. And that causes a great deal of interesting behavior, if you want. It's much more complicated, and it's somehow different in nature from what you get in the compact setting. I mean, you can construct examples like this. I think that if you take 1 over n log n squared, you get a picture like this. Okay? And that's much more complicated. I mean, yeah, it's much more complicated, and you can create lots of interesting behavior in the case of multifractal analysis when the situation is like this. You get phase transitions in the multifractal spectrum. That's what happened. That's not going to happen here because the pressure is very well behaved. But if you pick another sequence, another map, then you can create lots of trouble. Well, from infinity to finite, yes, it's convex. So you cannot be infinity, then finite, and then infinity again. Okay? But it's perfectly possible, well, in the case of the full shift, these are typical pictures somehow. If you get a different type of countable Markov shift, then you can create things as bad as you like. But the combinatorial structure of the shift somehow forces the shapes of the pressure that you can actually have, at least in this setting. Right? Okay. 1/2. Well, you were talking about Jannik's theorem yesterday, and maybe I should just explain basically what was the problem that people were interested in. I'll do it here. This is just a side remark that I'm going to make because several people talked to me about Jannik's theorem yesterday, so maybe I should just make the remark. So we know that if you pick x in 0, 1, then essentially this happens. But you can think of what happens with those points. You pick a tau larger than 2, and consider the set of points f tau, which are the points in 0, 1, such that this happens infinitely often, right? And what Jannik did was actually to compute the house of dimension of this. His proof is, of course, not dynamical, and it's not a hard proof. It's on Falconer's book, if you want. You just use smart covers, and you can actually compute it. So what he did is, if you have tau here, and you have the house of dimension of the points that approximately fast of order tau, meaning this set here, the picture you get is the following. If tau is more than 2, you get dimension 1 because it holds for true. And then it's of the form, if tau is larger than 2, then the house of dimension of f tau is actually 2 over tau. Okay? There is a point here in 2 where this function is not analytic. It's 2, which is very similar, if you like, to 1/2, which is where the phase transition of the pressure occurs. So what people wanted to do is, okay, maybe the fact that 2 is there in both cases is just not something random, but it is something to do with this phase transition, meaning that there is a relation between 1/2 and 2. So in order to try to make that precise, what you need is a different proof from Jannik's theorem. Jannik's proof is not dynamical in nature. So if you have, maybe, this is an idea, say that you have a dynamical proof of Jannik's theorem, maybe it's perfectly possible to relate this dynamical quantity here, the pressure, with the fact that this function here is not real analytic. And well, there's been work on that direction, Hill and Vellani, Urbanski, and so on, and they actually managed to construct a very sophisticated set of tools, shrinking targets and things like that, in order to prove that. They proved beautiful results, great results, but they did not prove this. So as far as I know, this is still not completely solved. Maybe it is, I don't know. That's what I know. I haven't worked on this, so I don't know. So, well, that's what I wanted to answer to you and you that were interested in this kind of questions. Well, I have nothing to say here because I don't know how to do it. So I just wanted to point out that maybe 2 is not just a casual number that appears here and here. Anyway, let me try to show you what I want to do today. Okay, where was it? So what I wanted to do today is something that's harder than what I've been doing, but for which the ideas are essentially the same. It's just technically harder. So what I want to show you is some results on arithmetic averages. Of digits of continued fractions. We know, so you pick a number, you have it written in the continued fraction expansion. So already in 1935, Khinchin it's actually the claim I'm going to put here is just like the last sentence of his monograph on continued fractions, showed that if you take the arithmetic average, so for Lebesgue almost every x, if you compute the arithmetic average of this is not finite. What he actually proved is that the lim sup is infinite. But you can show that actually the limit is infinite, Lebesgue almost every point. Okay? The way that Khinchin did it was essentially a Borel-Cantelli type of lemma. He showed that for Lebesgue, the argument of Khinchin, I don't know how to write this. He showed that for Lebesgue, almost every x, I'm going to restrict to 0, 1 because the rest is exactly the same. You know that there exists a sequence such that the digits in the continued fraction expansion are larger than this. So if you do the arithmetic average at order ni, it will be larger than the log of ni, and therefore for that sequence, the limit will be infinite. to show that the limit is actually infinity, you can use the same argument as Yuri Lima already showed us. But I'm not going to do it right now because I haven't defined even this as an ergodic sum, but this is an ergodic sum, and you integrate with respect to the Gauss measure, truncate on the first 10 branches, and then move on, and the limit will be infinity, and that allows you to show that this is actually infinite. It doesn't matter. The limit is infinite. And of course, you can pick up lots of numbers to show that this is actually infinity. If you pick, for example, for x equal to e, then the limit is infinite. Well, let's say e minus 2 so that everything is in the interval. Sorry? I don't know. I don't know. I don't know. I don't know now, at least. But of course, there are plenty of numbers for which this is a finite number. And if we keep it in the interval, this is just once. Therefore, the arithmetic average is only 1. You can do whatever you like to find any number you like. I mean, you have total freedom to choose the digit, so you can construct basically anything you like. This is it's a lower bound, though. Cannot be, the average cannot be smaller than 1 because the smaller digit that you're picking is actually 1. So what we're actually interested was in trying to compute the size of the following set. Pick all points for which the arithmetic average exists and it is equal to 12. And try to estimate the size of that. Okay? So the theorem is the following. This is joint work with Thomas Jordan from Bristol. It's the following. For every alpha, the set A of alpha is dense in 0, 1. But the interesting part is this one. If you look at the following function, alpha going to the house of dimension of the set A alpha, with alpha starting in 1. I mean, that's the domain of this function. Then this is a real analytic, strictly increasing, strictly concave function. And that's nicer, because what you get here is a bunch of sets, each of which is dense in the interval. So topologically, the composition is kind of complicated. But if you code it by its size, then the function is as regular as it can be. It's actually real analytic. This is a phenomenon that happens in plenty of things that are called multifactor analysis. This is by no means the first time that something like this happens, but it's still a remarkable fact. Let me draw the picture so you get an idea of how does the function looks like. So an upper bound for it is 1, where within the interval. Sorry? Well, for the purpose of house of dimension, rational numbers do not exist, so. Well, of course, if you have finitely many digits, you're in trouble, of course. I mean, you have only 10 digits and you take the limit going to infinity, yes. Yeah, let's be precise here. Against, how is it called? That are rationals but are not rationals. Okay. No, sure. Irrational numbers. I need an infinite expansion so that the average is not 0. That's the correct point, of course. And then, yeah, otherwise it will be discontinuous. I know what you, yeah, okay, of course. And this goes asymptotically to 1, right? Which is, I mean, I don't know if it's intuitive, but at least you know that Lebesgue almost every point is such that this limit is infinity, and what actually happens is that this goes very smoothly up to 1. The derivative here is infinity. It goes like this, okay? Strictly concave, real analytic, it's a very good description of the level sets that you have constructed this way. So I will of course, it depends on the measure you're interested in. Lebesgue measure of all these sets is 0. I can construct an equilibrium state supported in each of the sets. I'm going to follow exactly the same kind of pattern I did to show Besicovitch theorem, which is like have a variational formulation and then use thermodynamic formalism to find a measure that actually maximizes this variational equation, and then you will be very happy. We will be able to use all the properties of the pressure to conclude this. The fact that the pressure is real analytic is the reason why this function is real analytic. That's the type, basically. Okay? So I will sketch it only, but keep in mind, please, the detailed proof I did of Besicovitch theorem, because the ideas are essentially the same. Thing is here, the situation is a bit more complicated, but well, the idea is basically what we did in Besicovitch case. Well, the way this theorem is stated here is not dynamical, so I have to rephrase it in dynamical terms, meaning that I want this to be a Birkhoff average. Okay? So let phi be defined from 0, 1 here to n. Yes. You pick a number. And you assign it the first digit of its continued fraction expansion. Okay? Therefore, if you look at the Birkhoff average, I said uno of this, if you remind what I discussed yesterday, what did the Gauss map did was to take one. If you apply the Gauss map to this, what you get, T of x, is A2, A3, blah, blah, blah. So the Gauss map acts as the shift in the continued fraction expansion. Therefore, what you're getting here is the first n digits in the expansion. This is basically the lim over n, right? So in this way, we can, with this potential now, I have to choose a smart potential, this one, I can think of this set as a dynamically defined set. And now I can start playing with the techniques that we have developed so far. So, with this in mind, you can already prove that the limit is Lebesgue almost everywhere equal to infinity, just using the Gauss measure on the argument that Yuri gave us in his lecture, right? Okay. So as I explained at the beginning of the lecture, when you have these dynamically defined sets and you want to compute the house of dimension of it, you have like to do two different things. On the one hand, you need a variational formulation of the problem, meaning that the house of dimension of this set is the supremum of certain things. And then you need a way, in case it's possible, it's not always, but it is in this case, to find a measure that maximizes this variational formulation. So I will concentrate on the second part this time. I will ask you to believe this. The house of dimension of the level set of arithmetic average equal to alpha, it's equal to, let's put it this way, the house of dimension of measures where mu is an ergodic measure, and exactly as in the case of Besicovitch, I will ask this measure to be supported here. Now, yes? Yes, indeed, that's a very good point, because it's not exactly this the potential I'm going to use. I'm going to use a slightly modified version of that essentially involves alpha. Otherwise, you're absolutely right. There's no way I could come up with a measure that maximizes that set too. Sure, you're absolutely right. This was exactly what we have in the Besicovitch case, essentially. But unfortunately here, since we have infinitely many branches, you have to add an extra condition. And it's the following. I will ask this to be finite. Okay? Basically because what is the house of dimension of an ergodic measure for which this holds is nothing but the entropy over, I'm going to call lambda mu this, the Lyapunov exponent, mu ergodic, and supported in this set. Okay? So I want this to be, in this case, there are lots of measures that have infinite entropy, so I don't want to have the problem of divide infinite over infinite because I don't know how to deal with that. Okay? Sorry? What's mayor que cero, ¿cuál? Oh, well, you don't have zero measures in this case. It's the Gauss map. Second iterate gives you everything expanding. Well, it's general for hyperbolic cases and Holder potentials. All the other cases are more particular. If you pick a parabolic fixed point and you have to work harder, and it's in certain cases. Catherine has done work in that direction, and yeah. But then you have to work harder. Like a general theory works when thermodynamic formalism works well, that is, expanding maps, uniformly expanding, and very regular potentials hold it. This is close to it because the map is very good, but it has infinitely many branches, and the potential I'm considering is extremely good. Okay? But in general, you have to work hard. I mean, yeah. Okay. So that's the variational formula we have in mind in the first place. And now, I'll ask you to believe this. What I'm going to do is to construct a potential in the spirit of what you were thinking of. Of course, I need a supremum. Thank you. Yeah, sure. Otherwise, it's a set, and that's much more complicated. Yeah, thank you. So what I want to do is to show you how to construct a measure that maximizes this expression. I insist this is not trivial because this function is not upper semi-continuous, right? And here the situation is even more complicated, but because the space of invariant measures is not even compact, so the situation is even harder. But well, I mean, it doesn't matter. Okay, I'll try to show you how to construct then which is the right potential to choose to apply the thermodynamic formalism and show that you actually can construct an equilibrium state supported on that measure. Okay, so let Q be in R and delta be a number in 0, 1. And alpha larger than 1 fixed, which now appears as you were expecting. So I'm going to consider the following function, real function. Q alpha minus phi minus delta log t prime. Now I've made alpha appear in the potential that I'm looking at. It looks hard and you don't see really why would you ever consider a potential like that, but let me try to convince you that it makes sense in the following sense. Remark. We already know what is the house of dimension of the set. I don't have a measure supported on it, but I know that it's a supremum over all these measures that are supported on the level set, and I look at its larger house of dimension. So pick this. And suppose that mu q is an equilibrium measure for the potential q alpha minus phi minus house of dimension of A alpha log of the derivative. Okay? So let me stress that this is a function of q. So what you would get is the following. Variational principle, I have an equilibrium state. This will be the entropy of that equilibrium state plus q times the integral of our first digit potential minus alpha minus the house of dimension of the set alpha times the Lyapunov exponent. Okay? what we can immediately conclude in this setting is that this number is actually larger or equal than 0. Why? Pick a measure, ergodic, supported on A alpha, such that the Lyapunov exponent of that measure is finite. If a measure is supported on this set, what does that mean? It means that the Birkhoff average with respect to that measure is equal to alpha. Because the arithmetic average is equal to alpha, the arithmetic average is the Birkhoff average, and I'm supported here, I'm looking at the measures that for which this is actually equal to alpha. If the Birkhoff average is equal to alpha, Birkhoff ergodic theorem tells us that the integral is equal to alpha. In particular, this term here is 0, right? So, you get h mu q minus the Hausdorff dimension of A alpha h mu q, right? But we already know that this number here is the supremum of all ergodic measures supported by here. Well, okay, let me write it here. Alpha 1, right? That's what we have. That's a theorem I asked you to believe. If this was negative, so if h mu q minus the Hausdorff dimension of A alpha lambda mu q is negative, then I probably have a wrong sign. Then I have h mu q. I have a wrong sign. Okay. Okay, where's the... And there's no problem with that, of course. That's what it should be, but I want to have a problem. So I need the inequality to go the other direction. So the pressure, how is it? It should be like this. So that should be a plus. Okay. Well, if I have a measure supported on this set, then this integral is equal to alpha. So this value here is 0. So you have entropy plus this term here. Okay? So there's something I'm doing wrong, and I don't see what. This should be a minus. Okay. That's perfectly fine. Okay, I don't see it. Why is it this? So, okay, maybe I need a different measure in the computer. So that would be tangent to 0 no, but I know. No, it's so silly. Take the supremum of all those measures. That gives you 0. And you're taking the pressure over all invariant measures, so it can be larger than that. Okay. Okay. That's it. Good. Let me explain to you. I understood. Maybe you did not now. So, okay. We have this. What happens is, I know that the house of dimension of this, it's equal to the supremum of this, mu A alpha equal to 1. So if I want to show that the pressure of this is larger than 0, the pressure is, by the variational principle, is the supremum of the entropy of this term over all invariant measures, right? If I take a sequence of invariant measures for which they are supported here, and the supremum of entropy over Lyapunov exponent is actually the dimension, then I get that over that narrower set of measures, this expression is 0. Note, so that means what? There exists a sequence, mu n, of invariant measures, such that every mu n is equal to 1, and the limit h mu n lambda mu n is actually the Hausdorff dimension of the level set. Okay? That's the variational principle. That means that I can make this difference as small as I want. Okay? But since the pressure is considering measures that are not only small, as close to 0, that's what I mean. The difference is as close to 0 as I want, so in the limit is 0, but the pressure is involving more measures. So the pressure of, so this claims follows. Let me say it in a different way. I can find a sequence of measures for which this expression here tends to 0, right? Which is exactly this sequence. Therefore, the pressure is larger than 0. Okay? So, you're not convinced now? This, I hope that everybody's convinced that this I can make it as small, as close to 0 as I want. Okay? I know that the Hausdorff dimension of the set is the supremum over these quotients where the measure is actually 1, right? Yeah, okay. Mu. Right. So I can make this as small as I want. That means I can make the pressure as close to 0 as I want. Therefore, since I'm considering more measures than the ones that the sequence I picked here, the pressure can be higher. Convinced? Questions? It's a good moment to ask questions. Since no? You believe me? Good. Great. Hola. Okay, the pressure is not only positive, but I have the following picture. What I can actually prove is that if you pick Q, and here you have the pressure of Q alpha minus phi minus Hausdorff dimension of A alpha log of the derivative, the picture as a function of Q looks like this. More or less. Okay? It's not that surprising, because if you remember what we discussed last time regarding the tangents to the pressure, a tangent to the pressure here should be, say that you have an equilibrium state, and then you have minus Hausdorff dimension of A alpha, the Lyapunov exponent. This is a constant term that does not depend on Q, plus Q times the integral of the equilibrium state minus alpha, right? So what I'm basically saying is that you fix alpha. This is the slope of, if you want, this is the derivative of the pressure, right? These are the tangent lines to the pressure at each point. And this is the slope of that tangent. This is the derivative of the pressure. What I'm claiming is that for some values, this integral will be larger than alpha, and from some others, it will be smaller. And basically what you will get is a picture like this, that decreases and then increases. People in ergodic optimization will see this very clearly, because what they do is to take time to infinity to get the maximum of all possible integrals, in which case this will be larger than any fixed value. Therefore, the function will be increasing. And if you take Q to be minus infinity, or in this case, going to the phase transition, this value will be smaller than any fixed value because it's the minimum. Therefore, you have that shape like that. The fact that it's actually 0 in some point is slightly more complicated. But the fact that there is a tangent 0, that's fairly clear. It's increasing in some point and decreasing in some part. It's real analytic. At some point, it has to have a critical value. And the fact that this critical value actually goes to 0, that's slightly harder. But I have to conclude, and let me tell you how you finish now then the proof of this theorem. You do the following. Let mu q alpha be the equilibrium state for the potential q alpha phi minus alpha. Oh, well, I don't know. Minus the Hausdorff dimension of A alpha log of the derivative. We know that the pressure of this is 0. And we know two things. We know that the pressure of Q alpha is 0. And we know that the derivative of Q alpha is 0. The fact that the derivative is 0 means that the tangent to the pressure has 0 slope. The tangent of the pressure is this value here. This is 0. What does it mean? It means that this integral here is equal to alpha. What does that mean? By Birkhoff, that this measure, mu q alpha, is supported on the arithmetic level set. So this implies that mu q alpha, A alpha, is actually equal to 1. Okay? It's Birkhoff. The tangent is 0. So by Birkhoff, this measure is supported on the arithmetic level set of parameter alpha. But the fact that the pressure is 0 means that h mu q alpha minus the Hausdorff dimension of A alpha times the Lyapunov exponent of A alpha is equal to 0. Because this other term now vanishes. And that's great, because what do we have? We have a measure that is supported on the level set, and such that the quotient of entropy over Lyapunov exponent is exactly the house of dimension of the level set. Okay? So the spirit we have followed is exactly the same, a bit more confusing, as you can see. You have the variational formulation. That's one thing that you have to aim for, as in the Vesikovich case. And then you have to find a measure that maximizes that variational equation. In order to do that, tools from thermodynamic formalism are very useful. And that's why I want you to remember. The variational formula, first thing you need to prove in these cases. And second thing you need to do is to find a measure that maximizes that variational formula. And in order to do that, you need thermodynamic formalism. In the case of Vesikovich, it was fairly simple and straightforward, and we did all the computations. In this case, well, the situation is slightly more difficult, but the principle is essentially the same. Thing is, of course, you start dealing with potentials that are more complicated, and, well, but that's the nature of the problem. So I'm going to conclude, but the real analyticity of the function follows from the implicit function theorem, but, well, that's it. Thank you.